What if your body had a hidden flaw? Something you wouldn't even notice until it could be too late. Hi, my name is Alex, and today I'll be reviewing a case study about a 13-year-old boy who had no idea his heart was at risk because of something as simple as a calcium imbalance. A healthy 13-year-old boy with a history of prematurity complained of chest pain without any associated palpitations, dizziness, or syncope. He reported increased fatigue and weakness and bilateral hand paresthesia. An ECG obtained by his primary showed a prolonged QT interval of 495. He was referred to cardiology for outpatient evaluation, and he had a normal physical examination there. Before we move on, we need to discuss what a QT interval is first. This here is an ECG. Let's go over a few basics. An ECG, or electrocardiogram, records the heart's electrical activity. The P wave here represents atrial depolarization, the QRX complex shows the ventricular contraction, and the T wave here indicates ventricular repolarization. The QT interval here is what we want to focus on, and it is crucial because it reflects the time needed for the ventricles to reset. If it prolongs, it can lead to a dangerous arrhythmia. This is an example of a normal QT interval, and this is an example of a long QT interval. Long, you see, this is important. It's extended, it's longer. One more time, let's review. This is an example of an ECG, and this right here is the QT interval. The QT interval is the depolarization and repolarization of the ventricles. To do this, we need an influx and outflux of calcium ions. This is the important part of this case study that we'll get to in a second. We're going to soon learn that the patient had a low count of calcium in his system, and this prolongs the QT interval and will have an effect where we have an extended QT interval, and this can be dangerous. The graph behind me is an ECG, and it does not look like this. The graph behind me is showing a condition called torsade de pointes, and it can be a fatal heart arrhythmia that is caused by prolonged QT intervals. And that is why the prolonged QT interval can be so dangerous. Getting back to the case study, the patient was referred to a cardiologist, and the patient's prolonged QT was confirmed once again on a repeat ECG. Due to the second confirmation of the QT interval prolongation, blood work was now ordered. Here we see an extension for hypocalcemia. How exciting! Hypocalcemia, so low levels of calcium. And as we just mentioned, calcium disruptions can affect the heart. And right here it is. It's proven. It's affecting this patient's heart. For you health skeptics out there, you might be asking, how does hypocalcemia prove that this heart arrhythmia is happening to this patient? Let's dive into that next. I want to quickly go over the physiology of muscle contraction. So this is a neuron and sending down an action potentials. There are neurotransmitters here, most likely acetylcholine, that will be released and depolarize this muscle fiber here. The depolarization will travel down into this T-tubule here, and then there's these pockets next to the T-tubule with calcium, and the calcium will flood into the T-tubule. Once the calcium floods into the T-tubule, I want us to zoom in on a muscle fibril and talk about the thick filaments and the thin filaments and where the calcium binds on the thin filaments. And I'm going to let Armando Hasugian take over from here.
So just recapping, here's what our sarcomere looks like. And it contains the thin filaments and the thick filaments. The thin filaments in blue and the thick filaments in red. So let's get a portion of this thick filament, and this is what it looks like. And it contains many myosin heads, usually in doubles, as you can see. And myosin, the protein myosin, makes up the thick filaments. So each of these heads are part of a myosin molecule, you can say. And if we take a zoom or a portion of the thin filaments, this is what the thin filament looks like. And it's a bit more complicated in that the actin proteins are like twisted together like a helix. And there are also other structures, such as tropomyosin, which actually blocks the binding site of actin here, shown in green. And we also have troponin here in orange, which allows calcium to bind to it.
Did you hear that at the end? Armando was talking about calcium. And calcium, he was saying, comes over and binds to troponin on this receptor there, which then is connected to tropomyosin, and then which is connected to the thin filament. Here's the thick filament with the myosin head. So calcium comes in, binds to the troponin, which is connected to tropomyosin. This induces a conformational change. Then this exposes the thin filament for this myosin head to come up. And attach to the thin filament there. With a little bit of help from ATP, our energy buddy, we can have the thick filament connect to the thin filament, and it will pull on the thin filament there, inducing the muscle contraction. This is the basis for muscle contraction. And it all starts with this little guy here called calcium. This is what I wanted to drive home today. It's so important because if there are low levels of calcium, muscles cannot contract as they normally would. Going back, this makes sense why it would affect the heart. There's not enough calcium to make the heart beat, then we're going to have an arrhythmia. And that's what is happening to this patient. Before we move on about the why in this case study, why this patient was experiencing low levels of calcium, aka hypocalcemia, let's go back and just remember his symptoms again. One, he was having chest pains. So that could be going back to the QT interval prolongation we were mentioning earlier, but he was also having fatigue, weakness, and bilateral hand paresis. So this tells me that the patient wasn't just experiencing heart problems from the low calcium, but general muscle weakness and musculoskeletal weakness from the low calcium levels as well. So this patient required hospital admission for the management of his hypocalcemia. He then had some extra tests done while he was there, and they found a decreased parathyroid hormone, normal albumin, normal vitamin D, and a negative fluorescence for DiGeorge syndrome. And he was diagnosed with primary hypoparathyroidism. That's what this case is about, hypoparathyroidism.
Okay, so this is where the thyroid gland lives. It lives at the distal aspect of our neck. And then this is the front of the thyroid gland, and then this is the posterior side of the thyroid gland where the parathyroid glands in the thyroid gland live. In the parathyroid glands are these little pockets of cells called chief cells, and those are the cells that pump out the parathyroid hormone that then travels to the rest of the body.
Back to physiology. Why is the parathyroid hormone so important in our calcium regulations in our body? Let's talk about it. This is our thyroid hormone, posterior thyroid hormone, and these are our parathyroid glands, and they make parathyroid hormone. And PTH works on three main organs in the body. First, we have our bones. It activates the bones and the osteoclasts in the bones to break down the bone and release more calcium into the bloodstream. Second, we're going to move on to the kidney, and there's two mechanisms within the kidney. First, it acts on the distal convoluted tubule to reabsorb more calcium from the filtration system and put it back into the body. The second way is that on the kidney can activate vitamin D. Vitamin D then comes over to the colon and in a similar manner will tell the colon to reabsorb more calcium into the system. And in these three ways, you have more calcium in the bloodstream through these three mechanisms and how the PTH targets these three organs. Now, if we don't have enough PTH, let's say these get knocked out or something is going wrong, we're going to have low levels of PTH, and then we'll have low levels of calcium because the osteoclast won't break down bone. We'll have low levels of calcium being reabsorbed from the kidneys, and we'll have low levels of calcium being reabsorbed from the colon. So all in all, this puts us in a hypocalcemia state, just like the patient in this case study. Back to the case study. This patient was diagnosed with primary hypoparathyroidism. Primary indicates that it is something wrong with the gland itself and not something further upstream, let's say in the brain or a misstep elsewhere. So primary hypoparathyroidism is what this patient was diagnosed with. Then moving on to that, doctors decided that it was due to an autoimmune condition. So the body can make antibodies against the chief cells, which then reduce the output of PTH, which then affects calcium, and that is why the patient ended up in a hypocalcemic state. Let's move on to treatment. Thankfully, treatment for this 13-year-old is going to be pretty straightforward. For hypoparathyroidism, typically treatment is just supplementation with calcium. In this case study, he was discharged home and they gave him calcitrol, calcium carbonate, magnesium chloride, and arylcalciferol. And to conclude the case study, it looks like the patient here was lost to follow-up and then returned after 15 months, once again with a prolonged QT interval and recurrence of the fatigue feeling and the tingling hands. And then at the time he was put back on the calcium supplementation. And then after a 2-year follow-up from that, where he continued to follow his treatment plan, he was asymptomatic with a normal QT interval and normal calcium levels. In conclusion, this case study just wasn't about a prolonged QT interval. It was about the intricate, delicate balance that keeps the human body running. We explored how muscle contractions depend on calcium, how disruptions in that balance can silently alter an ECG, stretching the QT interval and pushing the heart towards arrhythmia. And the root of it all? Hypoparathyroidism. disrupting calcium homeostasis across bones, kidney, and the GI tract, setting off a chain of reactions that eventually reach the heart. It's a powerful reminder of how physiological systems are deeply intertwined and how one imbalance can send a ripple through the entire body. Muscle contractions, calcium signaling, cardiac electrophysiology, all converging in the single case, revealing just how fragile homeostasis can be. For clinicians, this case serves as a lesson in vigilance. Never overlook an electrolyte screening in case of a prolonged QT syndrome. You may save a life sitting right in front of you.